Okay, so another way to create, well, I would say generate electricity. Basically, usually we refer to this phenomenon as generating electricity. Generating electricity. And generating electricity. So what that is actually, I mean, as we talked about this, in the previous video as well. It's just you have a load over here, for example, a lamp, which is nothing but the resistance in a circuit. And then you in order for your, I mean, to put it in very simple terms, you want your lamp to start glowing. So you have to start you have to have some sort of source for the power. Otherwise, or in other words, you need to have some power supply, and that power supply is basically the part in a circuit that generates electricity. And what that means is that it has basically two poles. It has these two poles, and these two poles are basically, there is a difference of potential between these 2 points. And there was a water analogy that I once read in an electronics book, and that was actually kind of interesting. You see over here, suppose that you have basically a reservoir of water up here, and this reservoir of water has these poles or these posts over here. It's standing on these 2 stands or 4 stands, and suppose that it's basically it's a cube, for example. It's a cube, and in this cube there is basically, in this cube there is for example, there is water in here. And suppose that you take a pipe from the bottom of this reservoir, and there is a pond down here. Let's suppose that there is this pond down here, and in this pond you can basically pour water below the reservoir. And if I have these, let's suppose that I have this pipe coming down from the reservoir, and let's say that the reservoir is full of water. Now if I bring this pump over here, bring this pipe over here and give it to some sort of contraption, where, for example, you have something like a combination of an electric motor or a generator and some part where water can come in and go out. So suppose that the water can come in into this part over here and go out, go to the and basically pour into the pond down here. And as a result of the water coming down this pipe through this contraption over here, there is some sort of a wheel over here that starts turning as the water keeps basically as the water keeps flowing from this reservoir all the way to the pond. So when that wheel starts turning, there is there is a generator in here, and that generator, there is a shaft connected, for example, to that wheel, and then that generator starts turning, and then there is these two poles over here, and this gives you some voltage. This gives you some voltage, for example 220 volts AC or something like that, some voltage. And this voltage is basically some potential difference, and it corresponds to the potential, to the difference of the potential of water up here to the water down here. There is basically potential energy in the water up here in the reservoir. When that energy is released through basically rotating the shaft over here, there is a potential of difference between these two poles of the generator, and that generator then can be connected to a lamp. This generator can be connected to a lamp this way and this way, and then the lamp will start glowing. So you see, everything is working together. The potential of energy of water is converted into light or electrical energy through this whole construction over here. So that is basically called a potential difference. Now, in the previous video, we close my door. Okay, so now this potential difference, in the previous video we said that it could be, for example, it could be created chemically. For example, you have this battery over here, and there is this electrolyte inside a can, for example, and then there is two plates over here. These two plates, metallic plates, become the electrodes. And then that potential difference, of course, first you have to create it in the battery by charging the battery, and then that potential difference exists in the battery. And then when you connect this battery to a lamp over here, the lamp will start, of course, glowing, because basically this difference in the potential of these two electrodes has to be compensated, and that way this can be compensated. So that's basically the whole story here. Now this is, for example, chemically. There is also, for example, the photovoltaic generation of electrons. Of course, here it's saying photovoltaic generation of electrons. Technically, this could be, I'm not saying that it is, but technically this could be, I mean, based on what we know as physics, this could be wrong, because you cannot generate electrons. You can basically change their, well, let's not get into physics, but technically this label, or this way of talking about this thing could actually be wrong. You cannot generate electrons. You're basically changing the level of energy of electrons and level of energy of atoms and in different materials, and then based on that we have a potential difference. Otherwise, I'm not really sure, but I don't really think that you could really generate electrons. So yeah, but anyway, what that means, it doesn't really matter. That part really is not that important here. What's important here is that the photovoltaic part is basically those basically solar cells. You have seen those solar cells. These days they are very popular. Even there are many homes and houses that even basically factories or and such that are generating electricity that way, meaning that they put all of these solar panels on the roof of the factory or the house or somewhere where basically they can be exposed to sun, and then there will be some potential difference at the output of the solar cell, and this goes into, for example, some circuit which is called a charge controller. And then the charge controller will, using this voltage, will charge, for example, a battery. It will charge a battery, and then it does actually control the way that the battery is charged. It manages the battery and so on and so forth. And so then once your battery is charged, what happens is that then your battery is basically then connected to something called a UPS system, uninterruptible power supply. And what that does is that it takes, for example, the 12 volts DC, for example, or 48 volts DC, or basically 36 volts DC, or even 72 volts DC, and it converts this DC voltage to, for example, 220 volts AC, or for example 110 volts AC. And then that 110 volts AC that is basically the kind of the voltage that you have at a, for example, that would be a single phase basically power that you have at home, on which you run your refrigerator, you run your, for example, washing machine, your and all the other things that you plug into the wall plugs, basically. So that's basically that. So the photovoltaic part is this: occurs when light strikes semiconductor crystals, as in solar cells. When light strikes semiconductor crystals, which is something that we need to later basically take care of in physics. Right now we can't talk about that right here. So the next thing is the thermal generation. This uses temperature differences between thermocouple junctions. Thermal generation is used in generators on spacecrafts that are fueled by radioactive material. I see. So there is the thermal generation, and I don't really exactly know how this works, or based on which principle in physics it works. I don't know what that is, but it uses temperature differences between thermocouple junctions. So it uses temperature differences between thermocouple junctions. And this seems to be used in generators on spacecrafts that are fueled by radioactive material. This is I mean, advanced stuff, and hopefully we will talk about that hopefully soon in physics. There is also another way which here has been called the electrochemical reaction. Electrochemical reaction, which is this occurs between hydrogen, oxygen, and electrodes. Between hydrogen, oxygen, and electrodes. More about that in physics or chemistry. There is also the piezoelectrical. This involves mechanical deformation of piezoelectric substances. For example, piezoelectric material in the heels of shoes, power LEDs that light up when you walk. Now, I don't know really what these materials are, but if you want to research this, it's called the piezoelectrical and that is this is the mechanical deformation of piezoelectrical substances. Mechanical deformation of piezoelectrical substances, and it seems that this technology is usually used in the heels of shoes that power, for example, some LEDs that light up when you walk, and then I suppose, I don't know really what happens there. Not really important here, but nonetheless interesting. Now, the next thing that we need to take care of, is let's see, most of the simple examples was battery. As such, the source provides a potential difference to a circuit that enables a current flow. So basically, for the circuits that we use basically in this book, either in the theoretical illustrations or in the parts that we do basically using some oscilloscopes and things like that. Practically, we use a power supply, and you can think of that power supply as a battery. For example, suppose that you have a battery, for example, or let me draw a battery this way. Suppose that you have a battery, a 1.5 volts, for example, battery, and this battery has positive, for example, and negative. This is 1.5 volts DC. Now with this you can of course do a couple of things: power up some circuits, put a couple of them together. For example, put 3 of them together, you would get, for example, 4.5 volts if you put them back to back, end to end. For example, something like this, for example, positive to negative, and so on and so forth. And then if each of them is 1.5 volts, 1.5 volts, and 1.5 volts, then you technically you say that you have connected the batteries in series, and then the voltage over here becomes 4.5 volts, meaning that, which is equal to 1.5 times 3 volts basically. So that's basically what a battery is. Now the problem with the battery is that you cannot control the voltage of a battery or the current that is going that is coming out of a battery, or the current that it can basically send through your circuit. Meaning that if you connect a battery, for example, to a lamp, you connect the battery to a lamp, for example, a 1.5 volt battery over here, what happens is that depending on the resistance of this lamp, there will be some basically some current going through the circuit, and the current is basically going to be did we talk about the Ohm's law? No, not yet. But let's see. Oh, not yet. Okay. Usually, basically, what happens is that there is some voltage in a circuit, there is some resistance in a circuit, and some current in a circuit. Now, this current basically depends on the resistance and the voltage that you apply to the circuit. Now, directly you have no control over the current that is going through the circuit unless you had some way to control it. And of course, using a battery and for example, some load over here, there is no way to do that. So now, usually on an electronics bench, there is something called a power supply. So what a power supply does is that, first of all, your voltage is regulated. Meaning that, for example, you would get 0 to, for example, 25 volts DC. And you can change that voltage by turning a knob. Your output voltage is going to change and remain constant wherever you set it. And also your current is going to be regulated, meaning that you get, for example, 0 to 5 amps DC. Okay? And so what that means is that you can, for example, limit your current to, for example, 50 milliamp AC. So 50 milliamp DC, I'm sorry. 50 milliamp DC. And then the current that the power supply is going to supply to the circuit is not going to be more than 50 milliamp DC, and that way you can, for example, protect your circuit against, for example, burning something or frying something or something like that. So if for any reason you need to limit your current to any value, you can do so by, for example, turning a knob, and then your current will be set to that limit and will not exceed that limit. So we will use a power supply unit that I will show you in one of the videos when we are basically doing the first experiment here. Now, yeah, there is a couple of definitions here. We will go through these definitions, and then we have the Ohm's law that we will cover in just a few moments. Okay, so now as some sort of a definition, let's talk about the current, electric current. So basically the electric current, so as a definition given here, an electric current is a flow of electric charge. In the case of a battery, for example, electrons are the electric charge and they flow from the terminal. So in the case of a battery, or for example it's any sort of power supply for that matter, electrons are the electric charge. Electrons are the electric charge, and they flow from the terminal that has an excess number of electrons, and they flow from the terminal, excuse me, they flow from the terminal that has an excess number of electrons, to the terminal that has a deficiency of electrons. To the terminal that has a deficiency of electrons. This flow takes place in any complete circuit in a connected battery in any complete circuit that is connected to battery terminals. It is the difference in the charge that creates the potential difference in the battery. It is this difference in the charge that creates the potential difference in the battery. The electrons try to balance the difference, and we have talked about this. Now, because electrons have a negative charge, so electrons have a negative charge. Basically. So because they have this negative charge, they actually flow from the negative terminal and return to the positive terminal. So what happens is that, for example, if you have a lamp over here, and if you have a battery, for example, connected this way into this circuit, basically we said that since the electrons have the negative charge, this flow of electrons takes place actually from the negative pole of the battery. The electrons start flowing from this pole, and then if the circuit is complete, then they go all the way around the circuit, and then they come back to the battery, to the positive terminal of the battery. So then this direction of flow is called the electron flow. It's called the electron flow. This direction of flow is called the electron flow. Now, the problem with this electron flow is that this is, compared to what we have been doing in electronics and in electrical engineering and the related and everything related to that, this electron flow direction is actually fairly new, meaning that before this electron flow was discovered by physics, there was something called the conventional current flow. There was something called the conventional current flow. So the conventional current flow. Now this, I mean, this has a lot of, I mean, there is a lot of reasons behind this, and it kind of originates from Benjamin Franklin, and Benjamin Franklin seems to have been interested in physics and experiments in physics and things like that. Also, I think he's also known to have been interested in mathematics and geometry and things like that. He must have been some sort of a, I don't know, interesting person. I don't know what you would call that sort of person, but this person was actually into politics, into mathematics, into physics, into whatever you might think of, probably. And he used to, I mean, he's supposed to have been used to he's supposed to have been doing all of these experiments in physics, and I think it was around, for example, 1700s or so. And he was doing all of these or maybe a little bit later than that. He was doing all of these basically experiments in physics, and rubbing, for example, different types of cloth against, for example, glass rods and wax and wool and that sort of thing. And then there was some sort of a force between those objects, meaning that those objects either repelled each other or they attracted one another or something like that. And so based on that, then he, of course, back then they didn't know anything about electrons. Even the term electron most probably wasn't even around at that time, even in science. And, well, practically there was no science back then. I mean, no modern science really existed back then, because I suppose if the number that I have written here is right, then modern physics started with Newton. So it was, I mean, modern science hadn't even started yet. So what he did, basically, he used to do all of these experiments, and what he concluded from all of those experiments was that there was this magical invisible fluid that went from one material into the other material when you rubbed, for example, a cloth on a, for example, glass rod or something like that. And then they called certain things positive, and then they called certain things negative. And this negative and positive stuck in physics and in electronics and in electrical engineering and all of these fields. And then based on that, all of the amp meters and all of the voltmeters and all of the semiconductors and everything else were made. So everything was based on this conventional current flow. And what they thought basically was that basically the current was going from the positive terminal of the battery to the other terminal of the battery to the negative terminal. And they thought that basically the direction of current was actually this direction from the positive all the way to negative, meaning that this way, like this. So for many years, this conventional current flow was the norm in electronics and in electrical engineering and everything related to them. But then, after a while, then physics came up with all of the, I suppose in 1900s or so, around the time of Einstein, then all of those things about atoms and subatomic particles and all of those things basically were discovered by science. And so then basically science came up with the electron flow direction of the basically the direction of the flow of electrons in a circuit. Now what happens is that if you do for example a course in physics, everything is now based on the electron flow, meaning that in physics you do everything based on electron flow. But if you do any kind of if you read, most books in electronics are still based on the conventional current flow because of many reasons. For example, even the semiconductor, for example, schematic that we have today is based on the conventional current flow. For example, if you look at the schematic of a diode, for example, this is the cathode, this is the anode, okay? And you can see that this arrow, you can see that this is an arrow basically pointing in this direction, okay? Now what happens is that when you install a diode in a circuit, what's actually happening, the flow of electrons, the direction of the flow of electrons is actually the other way around, meaning that the electrons are going this way, but the conventional current flow is basically this way. And now everything in electronics is schematic, the diodes and everything are based on the conventional current flow. Now, long story short, what we are doing in this book, basically we are still basically into following the conventional current flow and not the electron flow, meaning that if you have a circuit over here, for example, if you have a lamp and if you have for example a power supply, something like this, and if this is the positive pole of the battery, the negative pole of the battery, what we assume and what we work with, we say that basically the current is going through the circuit in this direction and not in this direction. Not in this direction, but in this direction, which is actually wrong based on what's actually happening. Based on physics, this is wrong. But, well, in electronics it works for you. It's just like for example, in electronics we do everything wrong and then it works. All wrong put together becomes right. So that's something like that basically. So that's basically the whole story here. Now in the next video we will talk about the Ohm's law, and we will do some calculation using the Ohm's law and things like that. So I will see you in the next video, and thank you.